Today we will start with boundary layer theory. Boundary layer theory is one of the outstanding revolutionary theories that has come in the history of fluid mechanics, and we need to understand the perspective of this before coming to a conclusion how important or critical this theory has been. What is the motivation of learning this theory? Well, starting from designing aircraft wings to understanding how a cricket ball swings, how a bird flies, all these things can be well addressed if we know what is boundary layer theory and how to solve the boundary layer equations. So, that is the vastness of boundary layer theory, and it is a subject which can, if it is properly used, it can give rise to such a critical physical cum mathematical understanding of aerospace science and engineering, which cannot be really addressed by simply looking into the full form of the Navier-Stokes equations. Now, before getting into what is boundary layer theory, we have to understand that what is boundary layer, and then the theory aspect comes. So, to understand what is boundary layer, let us say that there is a flat plate infinitely long and we have just considered a finite length of it. It can be whatever length, let us say L, and fluid is coming from far stream with a velocity u infinity, uniform velocity u infinity. Now, let us consider what happens when the fluid interacts with the plate. Let us consider a section like this. So, let us say that at the wall there is no slip between the fluid and the solid boundary. This is a point which is questionable, because under certain circumstances it may become possible that fluid slips relative to the solid boundary. So, it need not be taken as a ritual, it is just a very common situation encountered in engineering. So, when you have this velocity as 0 at here, come to a point which is little bit away from this. So, the velocity here is non-zero, but it is not also u infinity, because the fluid here responds completely to the momentum disturbance imposed by the solid boundary and is arrested to rest. However, as you go further away and away, the fluid is not directly in contact with the solid boundary, but the fluid understands that there is a solid boundary. How does it understand? There is a messenger of momentum disturbance called as viscosity. Through that messenger, the fluid understands that there is a momentum disturbance. In this way, the velocity increases till it comes to u infinity and then the velocity does not change any further. So, this is u infinity, all these are u infinity. Come to another section. So, here at the same layer, whatever is this velocity will be even less. Why? Because more and more fluid is now in contact with the solid boundary. Then the velocity increases and the velocity reaches u infinity not at this height, but let us say some height which is here. So, or maybe here. This is u infinity and then it remains constant. When we say it reaches u infinity, remember it is from a practical engineering consideration, because theoretically it reaches u infinity only at infinity. Practically it may reach u infinity within a finite distance, and if it does that, then it simplifies our situation considerably. We will see that later on, but for the time being we are constrained to understand the basics of what is boundary layer. So, this circled location is the penetration depth up to which the effect of the plate is felt. Here this is the penetration depth up to which the effect of plate is felt. Outside, because of uniform velocity, the fluid really does not understand that there is a plate. So, now if we draw the locus of these circled points, then you come up with two regions. This region is a region where the effect of viscosity is important in terms of creating a velocity gradient. So, this is called as boundary layer. And this is called as edge of the boundary layer. So, in short we will write BL for boundary layer. This is the edge of the boundary layer. Let us say that at some distance x, this delta, we can clearly see that this delta is a function of x. So, the next obvious question will be that how large or how small this delta is. Now, there is a possibility that delta is very large. Can you tell when delta is very large? Delta is very large when the fluid is highly viscous. Then a large distance from the wall, up to a large distance from the wall, the effect of viscosity, the effect of momentum disturbance of the wall will be felt. However, if the fluid is less viscous, and this is what we are saying qualitatively, quantitatively we will identify some quantitative parameters, because less or more does not have any quantitative meaning. This is just a qualitative way in which we can bring out the physics. So, if it is very less viscous, then it may so happen that this layer is very thin, and how thin? Maybe delta at a given length L is much less than L. If that be the case, then we can develop a nice theory where we can solve simplified versions of the Navier-Stokes equation within this layer, and outside we can use simple potential flow equations or inviscid irrotational flow equations, which for constant density becomes Bernoulli's equation. So, the entire domain where ideally Navier-Stokes equation should have been used, gets reduced to a very narrow domain within which viscous flow equations, but Navier-Stokes equation, but in a simplified form, need to be solved, and outside that equation need not be referred to at all, and inviscid equation can be used. In the modern era of CFD, you people may argue that why is it necessary to get so much restricted, that is have a part of the domain in which viscous flow equation is solved, a major part of the domain where viscous flow equation is not solved. We can solve blindly the viscous flow equation, full Navier-Stokes equation for the entire domain. We have CFD tools, we have nice CFD software. Now you have to imagine the era in which this theory was developed. That era was a time when modern day high performance computing was not available. So when modern day high performance computing was not available, in those days, because machine was not beating human beings, human intellect was manifested at its best. So human intellect always tried to make an attempt to reduce the computational task by using judicious combination of physics and mathematics, and that was first attempted by the genius of a famous engineer known as Prandtl, and he came up with this revolutionary theory. I would say it is revolutionary because prior to Prandtl's era, fluid mechanics was governed primarily by mathematicians, and it was understood that there are certain classes of problems where exact solution of Navier-Stokes equation exists, that is fine. If it does not exist, people were debating about what could be possible solutions and all those things. Computational tools were not available, but those cases could not be addressed to come up with solutions which engineers could use for designing of devices, for example designing of aircrafts or designing of automobiles. These things were not possible until and unless this beautiful theory, which reduces the computational task to a large extent. Not only that, it gives a nice physical insight to the problem, that how large the domain may be, under certain cases we will identify which cases they are. There is a small part of the domain where viscous effects are important, and a major large part of the domain where you can use the dynamics of inviscid flow equations. The interesting thing is that although the fluid still has viscosity there, it does not have a velocity gradient, and that makes the shear stresses vanish. So that brings us to the perspective of studying the boundary layer theory. Now you people may have another argument, well, in Prandtl's era maybe CFD or computational fluid dynamics was not that developed. In the modern era, why do you require to study boundary layer theory? Because we can run CFD codes. Question is, let us say that you have a solid boundary, may not be as simple as a flat plate. Now when you have a solid boundary, to understand the velocity gradients at the solid boundary, you have to use very fine meshing or very fine grid points close to the solid boundary. But in the outer part, outside the boundary layer, such fine meshing may not be required. It will unnecessarily add to the computational cost. So there is always a question that how much distance close to the solid boundary you may have to use a fine grid, and how much and beyond what distance that fine gridding is not necessary. How will you know that? You will know that only when you can make an assessment of how thick it is for a given physical problem. Then only you will cluster fine meshes within that, and outside you will not unnecessarily put a huge computational burden by putting large number of grids. So the moral of the story is that even in the modern era of CFD, the physical basis of the boundary layer theory remains as important as it was when it was first introduced. So with this little bit of background, what we will do is, we will try to write the Navier-Stokes equation appropriate to this physical consideration. So, what are the considerations that we will keep in mind? So, our assumptions will be steady flow, then constant properties, that we will include homogeneous, isotropic, all these things just for the sake of understanding. Then Newtonian fluid, so that by a single viscosity we can describe the constitutive behavior. Then we will also assume that it is if it is constant property, then density is also constant. So, total derivative of density is 0, that means it will be incompressible flow. So, and we will assume the 2-dimensional scenario where x coordinate. So, if you have a plate like this, x will be along the plate and y will be normal to the plate. Now, you may argue that if you have such a case, then what will be your x and y? Still you have a global x and global y? No, in that case we will have a curve fitted x and y, that means x and y locally here, here x and y like this. So, in this way we will have a xy coordinate system where x and y are relatively orthogonal, but their orientations are continuously changing as you are moving along the solid boundary. So, with this, but for a flat plate it remains global x and global y. So, we are writing first the conservation of mass or incompressibility condition in this case. Okay. So, we will make an order of magnitude analysis. So, physically what we are considering, we have a boundary layer like this, at L we have a delta, free stream velocity is u infinity, so we will make an order of magnitude analysis of this equation. So, in this course so far we have discussed about what is order of magnitude analysis and we will apply that here. So, this is of the order of u infinity by L, this is of the order of, let us say at the edge of the boundary layer V is V infinity. Remember, the transition from the engineering theory to the mathematical theory has to be, so we call it just V infinity, just to give a name. So, we have a nice transition from a mathematical based theory to a engineering based theory. When we say mathematical based theory, this delta is technically infinity. Engineering based theory is that if the u here becomes 99% of u infinity, for all practical purpose we can assume that that is where the free stream condition is reached. So, you have a finite boundary layer thickness instead of a mathematically imposed infinite thickness. So, this is of the order of V infinity by delta. V infinity is V at the first stream. So, which is V at delta. Okay. So, now because these two terms are of the same order, these two terms must cancel each other to make it 0, they must be of the same order. So, you can write u infinity by L is of the order of V infinity by delta, that means V infinity is of the order of u infinity delta by L. So, one important thing that we can understand is that V infinity is much less than u infinity if delta is much less than L. But V infinity is never 0, no matter how much less delta is as compared to L. So, this is a big distinction between this and the fully developed flow. Fully developed flow, you have V equal to 0. Here V may be small as compared to u, but V is not identically 0. Some students have a misunderstanding that V is 0, because when we draw the velocity profile in the boundary layer, we only draw the x component of velocity profile, we do not draw the y component, but y component is very much there. If delta is comparable with L, V infinity and u infinity may be comparable, but in boundary layer theory we are looking for only those conditions for which delta is much less than L. So, boundary layer will exist for all viscous flow problems. It may be as small to as large as almost the entire up to infinity, but boundary layer theory is a theory which captures only those problems where delta is much less than L. The other part where boundary layer may be there, but boundary layer theory will not work. So, V infinity is much less than u infinity if delta is much less than L. Now, we will consider the x momentum and the y momentum. Because it is a steady flow and all, I am just writing the equation straight away. By this time you know how to write the Navier-Stokes equation for all. Let us assume that there is no body force, I am deliberately keeping a space here because we will make some order of magnitude analysis, for which I am keeping some space. So, let us find out the orders of magnitudes of these terms. So, this is of the order of u infinity into u infinity by L, u infinity square by L. This is of the order of V infinity into u infinity by delta, but from here you can see that v infinity is of the order of u infinity delta by L. So, this becomes of the order of again u infinity square by L. See, this is again something which is not intuitive. The reason is before that I think the pressure gradient term we have missed. So, let us just write this to complete the equation. So, coming back to this, so this term and this term, they are of the same order as we are seeing from here. Natural intuition is that because here is V and V is much less than u, if delta is much less than L, this term is much less than this. That is not true. Why that is not true is because this gradient is much sharper than this gradient. So, this term is exactly as important as this term. If you cannot ignore this term, you cannot ignore this term. Out of this term, these two terms, so this is of the order of, and this is of the order of, if delta is much less than L, then this you can neglect clearly. Pressure gradient we are not committing at this moment how big or how small it is. So, here also in the same way we will write the order of magnitude, this is U infinity V infinity by L. Using the continuity equation, this will also become of the order of U infinity V infinity by L. This is of the order of nu V infinity by L square, this is of the order of nu V infinity by delta square. Again this can be neglected. All these are based on the premises that delta is much less than L, the entire understanding is based on that. So, now let us write the inertia term is the left hand side in y momentum by inertia term in x momentum. This is of the order of u infinity V infinity by L by u infinity square by L, right. So, this is of the order of, so u infinity gets cancelled, V infinity by u infinity, that is of the order of delta by L. Similarly, viscous term, so this is much less than 1 if delta much less than L. Similarly, viscous term in y momentum by viscous term in x momentum is of the order of V infinity by u infinity, you can clearly see this term and this term. So, that is also same conclusion can be drawn from that. So, if this term is at least one order less than this term and this term is at least one order less, if this term is at least one order less than this and this is at least one order less than this, I mean because only these terms remain, this is at least one order less than this. So, the conclusion from here is a very important conclusion. This is the conclusion from the analysis of the y momentum equation. That being the case, you can write p as a function of x only. So, this will approximately become dp dx. So, this leads us to the boundary layer equations. From the Navier-Stokes equation to a simplified Navier-Stokes equation within the boundary layer, which are called as boundary layer equations. Okay. So, now when you have these boundary layer equations, question is when are these equations valid? To understand this, we will take the example of flow over a flat plate. Of course, we have taken the consideration that delta is much less than L. But a physical problem where some external condition is imposed, that does not understand what is delta, right. So, we need to express this in terms of externally controllable physical parameters. So, example, flow over a flat plate. Because there is no pressure gradient in the boundary layer you can write dp dx is equal to dp infinity dx, right. The pressure gradient along x is whatever is imposed from outside the boundary layer, and outside the boundary layer the beauty is that you can use this Bernoulli's equation if rho is constant. The reason is that the uniform flow is irrotational, outside the boundary layer is inviscid. Inviscid flow means irrotational flow will remain irrotational forever. So, you can use Bernoulli's equation with an absolute global constant. So, if that be the case, you can then differentiate this with respect to x, because u infinity does not change with x. If u infinity does not change with x, and that is what is the case for flow over a flat plate, you have dp infinity dx equal to 0. So, if dp infinity dx equal to 0, then you have this one. So, when you have this one, this is of the order of u infinity square by L, and this is of the order of nu u infinity by delta square. Okay. So, these two terms are of the same order. So, u infinity square by L is of the order of nu infinity by delta square. So, delta by L is of the order of u infinity L by nu to the power minus half, right. So, this means delta by L is of the order of Reynolds number to the power minus half. So, from here you have a clue. Now, this is an externally controllable parameter. So, you are able to say that delta is much less than L only when Reynolds number is large. So, boundary layer theory is applicable to large Reynolds number problem, because when you have Reynolds number large, how large? This Reynolds number such that delta is at least 1 order less than L, that is delta by L at least 0.1 or less. So, then you can find out a Reynolds number, and for that Reynolds number or Reynolds number beyond that you can use the boundary layer theory. So, delta much less than L will boil down to Reynolds number very large. So, boundary layer theory is applicable when boundary layer theory is applicable when delta by L is much less than 1, which is equivalent to Reynolds number large, and see another case which for flow over a flat plate is not encountered, but for other cases you have this dp dx, and this dp dx can play a very critical role. For example, if the dp dx is such that there is an adverse pressure gradient. Adverse pressure gradient means pressure is increasing along x. If pressure increases along x, then there will be a force which is opposite to the motion of the fluid. The fluid wants to move along positive x, but the pressure gradient, it is called as adverse because it is trying to oppose the movement. Along with that, the viscous flow also tries to slow the fluid down. So, the acceleration or the inertia of the fluid may not be sufficient to overcome these two forces, and if it is insufficient, the fluid instead of moving forward may start to move backwards along the negative x direction, and this is called as boundary layer separation. So, that is possible only if the pressure gradient is adverse. If the pressure gradient is favorable, then the pressure gradient will drive the flow along positive x, and boundary layer separation may not be possible. But boundary layer separation is possible if there is adverse pressure gradient. If there is adverse pressure gradient, then there is a chance that boundary layer separation occurs, and if boundary layer separation occurs, then there is no more monotonic growth of delta as a function of x, and then we say that boundary layer theory does not work. So, boundary layer theory is applicable when delta by L is much less than 1 and there is no boundary layer separation. This is not very commonly discussed, but this is very important. For flow over a flat plate this does not matter, because there is no question of adverse pressure gradient, the pressure gradient is 0. So, there is no question of boundary layer separation. So, today we have learnt that what is boundary layer theory, what are boundary layer equations, why it is important, and what are the assumptions behind boundary layer theory. We will take it forward from this in the next lecture. Thank you.